Okay, so for our last lab activity, for which you'll do a little report and answer some questions, we're building this circuit. So you've got an AC source right there. That's going to be our function generator in the lab. And in series with that, we've got two items. One familiar to us, our resistor, 22 kilo ohms, so 22,000 ohms. And a less familiar thing, a capacitor, which we've mentioned before and we've talked about a couple of times briefly. And the capacitor has this symbol and is measured with units of farad, so F-A-R-A-D, farad. And this is micro, so 0.1 microfarads is point and then 6 zeros and then a 1 farads. A 1 farad capacitor is a capacitor that has a lot of capacity. In other words, it can store a lot of charge, which means it can store a lot of electric energy. Okay? So remember that capacitors are essentially just two metal plates. You can kind of see that in the diagram here. That's what the symbol is meant to show, two metal plates. And when we apply a voltage to it, then that causes charge to accumulate on those plates. Now, previously we looked at accumulating charge in terms of like a DC voltage, where you just apply like a battery to it and you flow charge to it and eventually it charges up and then you're done. You can go and like release that electrical energy to power a camera flash bulb or something like that. Here though, we're attaching an AC source to it. So the direction of current in this circuit is first going one way, then the other way, then the other way, then the other way. And so first there's going to be positive charge accumulating on this side and negative on this side, and then the current's going to switch directions and it'll start accumulating in the reverse. But of course, at some time between there's going to have to be charge flowing away from one plate and towards another one. And so it all gets very complicated as to the effect of the capacitor on an AC circuit. But one important thing that we can do with a capacitor is introduce a phase shift between the voltage across the source versus the voltage across, say, the grab my pointer here, as compared to the voltage across the resistor here within the circuit. Okay, that is something we've not really encountered before. The idea that those two things could be different. And we'll talk a little bit more about phase, and some of the supplementary materials will also talk about phase. Okay, so if you haven't read any of that, you might want to stop now and come back to this once you've had a little bit of a look. But what we've got is our AC power source at 100 hertz, coming down through this wire, around over there, back over to here, and there it is. Okay, so attached to the sort of hot side and ground, though remember the polarity of the voltage and the direction of the current is constantly shifting when you've got an AC source. And we've got two probes coming from our oscilloscope. So we've got two inputs. One of the inputs is this one. You'll note that it's connected to the same places that the power source is. So essentially we're putting that probe, which is probe number 2, so the blue trace in our oscilloscopes, right across that power source. So it's just reading out whatever voltage signal the power source is putting into our circuit. And then over here, we've got the other probe, so probe number 1, which is going to be the yellow trace, across a, let's see, we've got red, orange, so that's 22,000 ohms, so 22 kilo ohms of resistance sitting here. And we're measuring the voltage difference across that thing. And then the other item we have in here, right, so there's our circuit, comes through this thing, goes across here, comes across the resistor, goes back out. You've got a capacitor. You can see really tiny lettering on there. It says micro 1J63. Honestly, the only thing we need to pay attention to in terms of the marking is the micro 1. That's 0.1 microfarads is what that translates to. They just put it in a particular notation. The mu takes the place of the decimal place, right? So it tells us the decimal place is in front of the 1. And then the mu also, the little sort of curly u, tells us it's microfarads rather than nanofarads or full farads or millifarads or whatever the case may be, okay? So there's our seemingly very simple circuit. And because the capacitor alternately accumulates charge when the voltage wave is rising and in a particular direction on it, and then allows charge to flow away from itself in the opposite direction when the voltage falls towards 0 and is getting ready to sort of go below the axis, right, and go to negative, this thing will shift the voltage signal that we read across the resistor relative to the voltage signal from our power supply, okay? And the amount that it shifts that those voltage signals is dependent on how big the capacitance is, but that's fixed, right? That's just a 0.1 microfarad capacitor, just like this is a 22 kilo ohm resistor. Different physical quantities, but the same idea. It's inherent to the capacitor. It's capacitance in farads, like the resistance of a resistor is inherent to the resistor. What we will shift around is the frequency, which we can do pretty easily. Right now we're starting at basically 100 hertz, and we're going to ramp that up and see what its effect is like, all right? And along with some background reading, looking at the effective frequency here, you should be able to sort out the answers to some of the simple questions we have. We're not going to go too deep on AC circuits, we just don't have the time, but I wanted you to have a little bit of exposure to that before we wound up the course, okay? So if we shift over here to look at the oscilloscope display, let me get in nice and close here. So remember that the yellow signal is the one, so let's see if I can point at it accurately. The yellow signal is the one that's being measured across the resistor, and the blue signal represents the voltage signal that is measured by the oscilloscope that's coming from the power source directly, okay? And yellow, since we're measuring that across the resistor, right, this voltage signal, if we use Ohm's law, would tell us what the current would look like in the circuit. And so what we're really seeing here is an offset in time. Remember, x-axis in an oscilloscope is time, between the voltage supplied by the source, the blue, and the current flowing through the circuit, the yellow. Okay? And this offset is because of the capacitor alternately storing up and releasing its charges, and thus its electrical energy. If we had no capacitor in our circuit, if we just had the resistor, well then we would have these two waves being exactly in phase. In other words, none of this little offset in time. They usually measure phase differences in terms of an angle. If you've ever had circuits before, you might have an idea of why that is, but just briefly, I mean, we're looking at sine waves here, so representing the offset in time between how one reaches its peak and another reaches its peak makes sense to put it in terms of degrees, because you're both looking at two sine waves, right? And the sine wave has a period of 360 degrees, and so if you're shifted by a certain number of degrees, then you know you're reaching your peak before or after another sine wave in comparison. Okay? So what we're seeing here are a couple of things. One, there's a significant time offset in degrees. It's about 35 degrees between the voltage supplied by the source and the voltage measured across the resistor, which remember is a proxy for the current in the circuit. One reaches its peak prior to the other, and that continues all along as it cycles back and forth. Okay? And remember, this is happening about 100 times a second, these cycles, because we're at 100 hertz. The other thing we're seeing is that if you look at the blue amplitude, so that's about 3.4 volts-ish, or 3.04. That's the blue, so that's a little taller, and a little shorter is the voltage signal across the resistor. And that suggests that the other things in the circuit, primarily the capacitor, has sort of an effective resistance that's using up a portion of the voltage, the difference between the whole thing applied to the circuit and what is being dropped by the resistor itself. Okay, so about, I guess, 0.6 volts in this case. Okay. So that's another thing. The capacitor essentially has an effective resistance. It's not a resistance like a resistor is resisting, because a resistor just dissipates electrical energy as heat, right? It just goes away. Whereas a capacitor, the reason it has an effective resistance is because it acts like a resistance. As you put more and more charge onto a capacitor, the harder and harder it is to push more charge on there, because you're having to, put another negative charge closer and closer to a bunch of other negative charges. And you can imagine if you have a ton of negative charges on there already, it becomes a lot harder to push that on there, that next negative charge on there, because of the Coulomb forces that we talked about right at the beginning of the course, because of the huge Coulomb forces that we get between those charges. So eventually the power source just won't have enough energy to push any more charges on there, and the capacitor would be fully charged, quote unquote. That never really happens in an AC circuit. These oscillations are happening so rapidly that the capacitor never fully charges up or fully discharges. But that little bit of reluctance to add charges is sort of the source of this apparent resistance. It's called reactance, and we'll look at it in just a few minutes. Okay? So this is what the relationship between the two traces looks like, the relationship between the voltage supplied to the circuit and this proxy for the current through the circuit, which is the voltage across the resistor. Now, if we take our frequency and we raise it up to, let's say, 1,000 hertz, really go for it here. Oh, we have to go over here, we have to click that, go into a different regime. All right, close enough. 1 kilohertz, right? Or 1,057 hertz, I suppose. Okay, we come back over here. All right, so a couple of things. I can't even see the yellow trace, so something is different. One, we've got a whole lot more periods here, so let's change our horizontal scale. So we go over here. So we just have a couple of periods in there, like we did the last time. And there we go. Now you can now that we've zoomed in a bit, we can see that there is still a tiny little, tiny little offset right there between the two traces, okay? But it's a lot different looking than it was at 100 hertz. So lower frequency, 100 hertz, bigger offset. And in addition to that, you'll notice that there was a bigger difference between the amplitude of the power supply's voltage signal and the amplitude of the voltage drop across the resistor, this thing that we're sort of using as a proxy for current in the circuit. Okay. Right now, the resistor is basically dropping every last little bit of voltage applied to the circuit. Okay, one occasionally is higher than the other. That's just measurement error. You see they flicker back and forth between 3 and 3.04 as time goes by. So that's, basically it's dropping all of the voltage, which means that at this frequency, this 1 kilohertz, that's suggesting that the effective resistance, this reactance of the capacitor, is basically nothing. I mean, it would be detectable if we really wanted to get super accurate about it, but it's essentially nothing compared to what it was when the frequency was 10 times lower. You'll also notice that we do have still a slight phase offset. So in terms of degrees, it's bouncing around a lot because of measurement issues, but right around 5 degrees. And you do see a slight offset here on the time axis. I wonder if I zoom in one more, whether we can get a better number. Come on here. No, because we're not showing, it gets confused when we don't show a couple of periods when it does its calculations. So back out again. In any case, just enough to show us that there is still a slight offset. Now, instead of zooming in on the frequency knob, I'm now gonna mess around with the frequency knob and just keep our eyes on the screen. So we go down in frequency, okay, and I'll adjust this so we keep getting a couple periods on the screen. As we go down in frequency, back to about 100. We're still a little bit over 100 right now. There, right about there is 100 again. So we're back to where we used to be. We got that 35-degree offset, so a significant time axis offset between the two. And we see that our effective resistance of the capacitor has gone back up, right? Not all of the voltage is dropped by the resistor, just sort of a majority of it, right? But pretty clearly the height of one signal relative to the other has changed. If we go up in frequency again, go way up to, I don't know, 3 kilohertz. Change our scale again. There we go. So now we're at 3 kilohertz. The phase offset, right, the phase offset right there is even smaller than it was at 1 kilohertz. Okay? And again, the resistor appears to be dropping every last little bit of voltage that we're supplying to the circuit. If we, again, really zoomed in, and you can kind of see that there's a tiny little offset here. You can barely see the yellow trace out from underneath the blue one between the two. Okay? So what is this telling us? This is telling us that at high frequencies, the capacitor acts more or less like it isn't there. Okay? So as the frequency goes up, the apparent resistance, the reactance of the capacitor, must be going down because the resistor appears to be dropping all of the volts supplied to the circuit. Right? The yellow trace is just as tall as the blue, in other words. And as we go down in frequency, the reactance or apparent resistance of the capacitor goes up, giving us a larger shift between the current and the voltage, the current in the circuit and the voltage applied to the circuit from the AC source. And also the resistor, right? The resistor here is dropping all the volts, but at low frequencies, the resistor only drops a portion of the volts applied to the circuit, suggesting that the capacitor's apparent resistance, so reactance, is actually relatively high at low frequencies. So the key relationship in all of this is, let's see if I can do this while holding this. If not, I'll put it down. So the key relationship in this whole thing comes down to this equation right here. So this is the, yeah, that's not going to work. Okay, pardon me. Okay, here we go. Backed up just a little bit. Yeah, I'll be fine. I'll just things just here. So hopefully you can still hear me. Okay. So let me move this equation down. So x sub c is equal to 2 pi fc. Okay. And this is the wordy version is capacitive reactance. You can just call it the apparent resistance of the capacitor, but x sub c. And that's equal to 1 over 2 pi frequency times capacitance. Okay? So for us, capacitance is 0.1 microfarads fixed. Okay? Right? We can't change that. And, well, not without changing our capacitor. This is the thing we've been messing with, right? This is the frequency in hertz. And let's look at that. So we were observing on the oscilloscope display that when we had low frequency, we had high apparent resistance for the capacitor. So according to the equation, when we have low frequency, that makes the denominator here smaller. That means that we're going to get a larger capacitive reactance, or apparent resistance of the capacitor. Great, that checks out with what we were seeing on the oscilloscope, because at low frequencies, only a portion of the voltage was dropping over the resistor, and the rest of it must have been dropping across this apparent resistance of the capacitor because of the loop rule. The other thing that we don't see out of this equation is that phase relationship between the current in the circuit and the voltage being applied to it. Though that is also related to the size of this capacitive reactance. If you have a larger capacitive reactance, then you're going to have a larger phase angle between, or time offset on the x-axis of the oscilloscope, between the voltage applied to the circuit, so the blue trace, and the current, or the voltage drop across the resistor, okay? But the current through that circuit that we're looking at, okay? The actual relationship is the phase angle, if I can remember this from the top of my head, it's something like inverse tangent XL over XC divided by R, something along those lines, okay? But it's not important, okay? All we need to know is that it's directly proportional to how big that capacitive reactance is. And so the idea that the lower frequency gives us a larger phase angle, larger time shift of voltage applied to the circuit versus current through the circuit checks out, all right? So when you have reviewed the supplementary materials, there is going to be a little report that you have to do for this. And when you've reviewed all that stuff, you should be able to answer the relatively simple questions, I think, outside of our experience from lecture, but good to get a little exposure to this kind of stuff. And with that, I will talk to you another time.